Hi everyone. So this is part 2 of our NoSQL project, and in part 1 we had completed the MongoDB part of it, MongoDB pipeline, and I along with Abhik and Harsh are in the team. So now we'll be proceeding to part 2. So this is part 2 of our NASA HTTP logs ETL project. In part 1, as I said, we implemented the MongoDB pipeline. We also uh, did as per the promise statement suggests that we ingest the official July and August logs, process them in batches, pass the records, detect malformed records, and run all the 3 queries and load the results into Postgres. So the part 1 full MongoDB ran on like 34 lakh records. I don't remember the exact figure. So I can actually show you the report. I can actually show you the report later, the compressed report. So in part 2 we have extended this from only MongoDB into a unified multi-pipeline framework. So the system now supports MongoDB, Hive, Pig and MapReduce all from one common interface. So as you can see here in the script itself, we have Hive, MapReduce, MongoDB, everything. There's Postgres. So we have all the things here that are required, and this is the source. So these are the 4 backend implementations. Each backend follows the same logical contract: load raw NASA logs, apply batching, clean and pass records, detect malformed records, compute the query results, and return normalized output for Postgres reporting. So the project set to use a menu-based system, so I can actually show you the system. So this is the menu-based system. So this is the we get the option run pipeline, show report, initialize Postgres, download official dataset, and exit. So we can actually run the pipeline, and we have 4 pipelines here: Mongo, Hive, Pig, and MapReduce. The next member, which is Harsh, will be showing the actual running of the live running of the pipeline. For now, I'll be only showing the menu. So let me just quit it. So these are the 4 pipelines, and in any pipeline we can let's say if we select Mongo, we can actually select how many queries or which query to execute, whether all queries are to be executed or only query 1, which was the daily traffic summary, query 2, which was top requested resources, and query 3, which is RD error analysis. So we could choose anyone, which is I'm choosing one here, all, and we can set the manually set the batch size. By default it's prompting you to set it to 1 lakh, but we can set it to any figure. The default input files are the files that I have already downloaded the gz files, and then you can use these input files. Run id, you can use anything, or blank for it will be generating its own Mongo, generating its own id. So for the rest of the demo, we already have pre-run outputs for Mongo and Hive, and as I said, Harsh will be running a live pipeline. So to avoid wasting time, I'll just show you the full dataset that was processed. Command. So yeah, see the run id p2 Hive all. It's a Hive pipeline, or the query ran successfully, all queries, 34 lakh 616 records, 35 non-empty batches, malformed records 1862, and runtime is as you can see. So our malformed records are quite greater when we consulted with our friends. So that's because we have used a stricter version of regex for rejecting the records, and these are just the results: the P2 Hive, P2 Hive and P2 Mongo. So now, compared to part 1, we have added pipeline switching, query selection, and multiple execution backends. First we only had MongoDB. So the next section will be demonstrating an actual pipeline run and the actual generated report, which will be done by Harsh.
Hello everyone, I am Harshvardhan Singh. My roll number is IMT2022101, and I'm also one of the members who was working in this project. So now I'll be running a live pipeline execution to show this part in action. So I'll use the MapReduce pipeline, which is one of the 2 new backends added in part 2 of the project. The 2 earlier backends, as one should have already explained, were Hive and MongoDB. So I'll just show you step by step how it runs. So so first we will be running with the menu, that is we need to type NASA log ETL, then menu. So you will see that a menu comes. So we need to run the pipeline, which is of MapReduce. So we will be selecting option 1. So here we are having 4 options. I'm selecting MapReduce, that is option 4. This is the Hadoop based backend that uses explicit mapper and reducer scripts to process the NASA logs. Fine. Yeah, so now I'm selecting query 1, which is about the daily traffic, and this part allows us to select individual queries or run all 3 at once. Here I'm just running the query 1 to keep the demo focused and does not take a large amount of time. Yeah, So batch size I'll be keeping as 1 lakh. This controls how many log records are processed per batch. The system track results per batch in PostgreSQL. And these are the user input files. These are the official NASA HTTP logs for July and August 1995, and over 3.4 million records are combined. I'll use the default input files here. So I'll press Y here. So yeah, so now I'll need to generate a run ID. So run ID should be meaningful, so that if I look again on this particular run ID, I'll know that I generated the results outputs for query 1 of MapReduce. So what run ID I'm thinking to have here is that P2 underscore live underscore, let's keep it MapReduce, and since we are running query 1, I'm going to use clue1. So yeah, let's enter this. Okay, so now we are having two options here. One is local and one is Hadoop streaming for MapReduce. So MapReduce has two modes, as you can see. Local mode uses the Python's multiprocessing Hadoop streaming, multiprocessing, whereas Hadoop streaming submits the job to Hadoop using the streaming API. This is the real distributed computing mode. So that is why I'm only selecting the Hadoop streaming, since local is simple only. So let's select the Hadoop streaming mode, and I need to keep the MapReduce artifact, so I'll select as Y here, and the command I'll select it as default. So I press enter, and here it is asking me to input the streaming jar file. So the Hadoop streaming jar, it is the bridge that lets the Hadoop run Python scripts as mapper and then reduce the mapped items. So so I'll be giving the this path of the jar file, which is opt on my machine, since it's a Mac, so homebrew, then opt again, then Hadoop libexec, after this it's share, then Hadoop, then inside tools lib, and inside lib Hadoop streaming 3.5.0 dot jar. Yeah, so now you see the pipeline is running, as you can see on the screen. So the MapReduce job is now running under the hood. Hadoop is launching a local MapReduce job. The mapper script reads each raw NASA log line and parses it using a regex and emits structure key valued pairs. The reducer then aggregates those pairs to compute the daily traffic counts for query 1. Notice that the same three queries, daily traffic, top resources, and hourly error rates, are defined consistently across all the 4 pipelines. And whether you run MongoDB, Hive, Pig, or MapReduce, it doesn't matter. You get the same query logic and the same output schema in the PostgreSQL. And since I'm only showing you MapReduce due to shortage of time, Vansh at the end will also show you the complete output for all the 4 pipelines. So this is the core design in part 2, a unified multi-pipeline framework with a single interface and a consistent query definition and shared reporting layer. So as you can see, the running is complete. I can show you the report also. See, so show report, I'll click on Y. So let me just enlarge this. Yeah, so you can see here all these things. So the run has been completed successfully. Let us just walk through the report. So the total records you can see here is that around 3.4 million total records are there. Then malformed records are also around 1800s. So it means that about 1800 lines didn't match the expected log format and were counted, but these were skipped. And non-empty batches here you can see is 19. So with batch size of 1 lakh, the 3.4 million records were split into 35 batches. Then runtime, here you can see that in milliseconds 29,404, and at the very bottom you can see the query 1 results also, daily request counts from the NASA logs. This, yeah, so this ends the output. So I'll just exit from the menu, and on top of this I can also show you one thing. So just let me type it first, scripts slash MapReduce. Yeah, so you can see here that unlike the other pipelines, MapReduce uses the explicit Python scripts, a mapper and a reducer, which you can see here, mapper.py and reducer.py. The mapper parses each log line and emits key value pairs. The reducer aggregates them. These files are what Hadoop distributes across nodes in a real cluster. So I can also show you some of the few first lines of the mapper file. So let me just show you that also before ending my part. It has already gone too long. Scripts MapReduce mapper.py. Yeah, so you can see here the first 30 lines of the mapper file. Here you can see the base log pattern and the request pattern. So this is a two-staged parsing that we have applied here. One is the a coarse parse and one is the finer parsing, that is the request pattern. Yeah, so this was all from my side. Now Abhik will continue for the next implementation.
Hello, I am Abhik Kumar and I will go directly into the PostgreSQL database to prove that all of the data actually landed in the correct tables and to show the batch tracking and reporting structure that part 2 adds. I have already run all the commands here for the sake of time. Now we can see that the reporting database has 5 tables, 2 metadata tables, ETL runs and ETL batches, which track every pipeline execution and every batch within it. The other 3 tables store the actual query results, daily traffic, top resources and hourly error rates. This is the relational reporting layer that part 2 adds on top of all 4 pipelines. Now the ETL runs table stores one row for every pipeline execution. You can see columns for run ID, pipeline name, query name, status, batch size, total records processed, non-empty batches, malformed records, and runtime in milliseconds. Every pipeline, MongoDB, Hive, Pig, and MapReduce writes to this same table. Now the ETL batches table stores one row per batch run. It tracks the batch ID, how many records were in that batch, and how many were malformed. This gives us per batch visibility into the processing. Now this is the result table for query 1, daily traffic. Each row is one day's request count tagged with the run ID so that we can filter by pipeline and run. This is the query 2 table, which stores the most frequently requested resources. And finally the query 3 table, which stores hourly error rates. All 3 query tables share the same run ID foreign key design, so the results from different pipelines never mix. Now I'll show the run metadata. Yeah, so here is the run metadata. You can see the run ID P2 live MapReduce Q1 that Harsh just executed. Now here we have the columns pipeline, which is MapReduce. This confirms which backend ran. Query name Q1. Harsh selected daily traffic only. Status is completed. The job finished successfully. Total records are 3.4 million. This is the full NASA July and August 1995 log dataset. Malformed records are around 1800 lines, which did not match the expected log format. These were counted and skipped. This matches the number from part 1, which confirms our parser is consistent across pipelines. Then non-empty batches. With a batch size of 100,000 and 3.4 million records, the data splits into 35 batches. And then finally the runtime milliseconds, which is the total time the job took, stored here for comparison across pipelines. Now I'll show the batch processing behavior. So this table has one row per batch for the run we just executed. Records are split into batches purely by record count. With a batch size of 100,000, records 1 to 100,000 goes into batch 1, records 100,001 to 200,000 goes into batch 2, and so on. Now the formula here is batch ID is equal to floor of record number minus 1 upon batch size plus 1. So batch 1 has 100,000 records, batch 2 has 100,000 records, and so on, and the last batch has whatever remains. You can see that in the records processed column. Now we see the query specific loading. So here we can see that Harsh ran only the pipeline with query 1 selected. So only the query 1 daily traffic table has rows for this run. Query 2, Q2 and Q3 shows zero rows. This proves that the query selection works correctly. The system only computes and loads the query you asked for. It does not run all 3 every time. If you run with query all 3 tables get populated. If you run with query Q1, only Q1 gets data, or if query Q2, then Q2 gets data, and similar for Q3. This is one of the key features added in part 2, per query control over what gets computed and stored. Now here is the report command. So finally the part 2 it also includes a built-in report command. This pulls all the metadata and results for a given run and formats them in one place. You can see the runtime, batch size, runtime batch stats, malformed record counts, and the query results all from a single command. This report reads from the same PostgreSQL table that I just showed you. So everything is consistent and the database is a single source of the truth. Here are all the tables. So this is the table for query 1 which we ran. Thank you.